Now, let's look at the SANCO2 system itself. This is a unique system with the highest efficiency of any water heater on the market. With a stated energy factor of 3.34, 1 kilowatt of energy in the form of electricity input will yield an average of 3.34 kilowatts of energy out in the form of hot water. This is dependent on a couple of factors, but under reasonable ambient temperatures, we've seen COPs higher than 5. SANCO2's split system has the best low-temp hot water performance of any heat pump water heater, capable of heating water at ambient temperatures down to minus 20 degrees Fahrenheit and beyond. This makes the SANCO2 applicable to any climate we see in the US, and a good portion of Canada too. This system also touts the highest first-hour delivery rate and the highest delivered water temperature of any water heater available. With a range of output temperature set points, we have the potential to store lots of hot water. With 175 degree Fahrenheit tank temp, we get about 142 gallons of 125 degree Fahrenheit hot water out of the 83-gallon tank. If we store more than enough hot water to meet peak demand, we can afford a 4-hour recovery time. And this new hot water is delivered straight to the top of the stratified tank, available for immediate use. Here's a diagram of a study that demonstrates how the SANCO2 performs under various conditions compared to competitors. This is taken from a Canadian study of real-world performance over the course of 12 months. The SANCO2 split system is put up against a hybrid system that is ducted to and from the outside, so ambient air temperature will affect the coefficient of performance of both. The bottom line represents a standard electric resistance water heater with a constant COP of 1. The blue and orange dots represent the SANCO2 and hybrid water heaters respectively, with the larger dot size meaning a higher water draw. As you can see, there is a consistently higher COP with the SANCO2. On average, the SANCO2's COP was 2.69 in the study of a cold Canadian climate, compared to the hybrid's 1.79. Performance would be even better in the warmer US zones. Both options are better than the electric resistance water heater, but the SANCO2 can be about 1.5 times more efficient than the standard hybrid model. Now let's look at the power usage of this unit. The blue line in this lab test represents the SANCO2's power draw over time, with a red dotted line indicates the outdoor ambient temperature. This study included a simulated water draw of 139 gallons in a day, enough to deplete the entire tank. To deliver 143 degree Fahrenheit water at 65 degree ambient temperature, the SANCO2 unit only operated twice at about 1,000 watts each time, and for only 5 hours, consuming about 5 kilowatts of energy in total. This next graph shows how ambient air temperature will change the input power required to meet the SANCO2's 4.5 kilowatt output capacity. In this example, where the ambient air temperatures are below freezing, you can see that to reach the same output capacity, the unit needs to use more energy to extract the same amount of heat from the cooler air. But even at these lower temperatures, the SANCO2 maintains the same 4.5 kilowatt output capacity, albeit at a lower COP. All these features add up to greatly reduced energy costs and reduced strain on the power grid. This system can even be integrated into a demand response program, thanks to the large storage capacity of the tank. To take advantage of cheaper electric rates or solar PV production, it's possible to manually program the SANCO2 to only operate during off-peak hours. It's important to understand the operation and installation of the unit and how it works so you can know how to make it work for domestic hot water and home heating. Here's a diagram of the gas cycle. This is a monoblock style system, meaning high pressure refrigerant comes factory sealed within the outdoor unit and the entire refrigeration cycle takes place outdoors. No refrigerant lines running between the compressor and the tank means this unit can be installed by any plumber. Municipal water enters the tank at 3/4 inch inlet at the base of the tank. A second fitting near the ground will be reduced from 3/4 inch to 1/2 inch, flowing from the tank to the outdoor unit. The water is heated up and sent back over a 1/2 inch line near the top of the tank. The tank fills from the top down, remaining stratified where the hot water stays on top and the cold water stays on the bottom. When the hot water reaches the inlet and the inlet temperature is measured at 120 degrees Fahrenheit, the outdoor unit kicks off, knowing that the tank is filled. Hot water is then drawn off the top of the tank for use, gradually filling from the bottom up with cold water. This cold water column reaches the thermistor around the center of the tank, and the unit kicks on, repeating the cycle. In the stratified tank design, thanks to a very high temperature gradient creating a boundary layer, the hot and cold water don't mix. The stratification is necessary for efficient operation because this heat pump relies on taking very cold water and bringing it up in a single pass with a delta T of 100 degrees or more, and this water is deposited directly to the top of the tank. The large volume storage, coupled with a slow and efficient recovery, is perfectly suited for single-family homes along with commercial and multifamily residential applications. We're going to go into more detail in a subsequent presentation, but these systems can be exceedingly efficient at delivering hot water to many people. Simply size the tank based on peak demand and size the number of heat pumps to be able to fill the tank back up again in 4 to 6 hours, depending on occupancy. This unit is designed to produce hot water only and will not produce cold water. This is because the great pressures needed to reach CO2's transcritical state make it prohibitively expensive to include a reversing valve. So, as you can see, there are a couple of different factors that affect the efficiency of this unit, with outdoor ambient temperature being one. Here you can see the COP drop as outdoor ambient temperature drops. Right around 68 degrees Fahrenheit is the optimal temperature for hot water production, indicated by a very high COP. As the temperature drops, the COP drops, but not too much. Even in the single digits, working at its hardest, this unit is still 2.5 times more efficient than an electric resistance water heater. You can also see the output capacity is always going to be 4.5 kilowatts or 16,000 BTUs per hour until you get down to about 5 degrees Fahrenheit. At temperatures that low, it does lose a little bit of capacity because it's working pretty hard to extract that heat from the ambient air. Another factor that affects the COP of this unit is the inlet water temperature. The CO2 refrigerant cycle works best when it has a very high delta T, where the water temperature is raised from 50 to 150 degrees Fahrenheit in a single pass. If that delta T drops, you're going to see reduced capacity and reduced efficiency. This is because the compressor is still working just as hard to bring the CO2 to critical pressure, but the quantity of energy transferred to the water is less, given that it started out at a relatively high energy level. We can see in this graph, higher inlet water temperature equals reduced COP. You might think it would be the opposite, and higher inlet temps would equate to less work done by the unit and more efficient operation, but that's not the case. The higher the inlet water temperature, the less efficiently the unit operates. This is never a problem in a domestic hot water situation, because you will always have this stratified tank where you're drawing in cold water from the bottom of the tank and using hot water from the top. However, this can be an issue in home heating situations, where return water temperatures can be high. Now let's address sizing for domestic use. We have 3 tank sizes available: a 43-gallon tank, an 83-gallon tank, and a 119-gallon tank. Because of the range of output temperatures, we have a wide variety of scenarios that the system can manage. Keep in mind though, the higher the output temperature, the slower the recovery time. Suffice it to say, the 83-gallon tank at a mid-range output temperature will get you 152 gallons of water at 110 degrees Fahrenheit, or about an hour-long shower. What about recovery rate? How long will it take to fill the tank back up once it's depleted? Well, the 83-gallon tank will fill up in about 4 hours. Can we use recirc with the SANCO2? A lot of the recirc systems we've seen work well with a gas boiler system, but fail when paired with a heat pump. We must be very careful to maintain tank stratification when installing recirc, but it can be done. The best option is to use a push-button system with an aquastat shutoff. Timed or smart systems don't work very well with the SANCO2. Some buildings, especially multifamily structures, must utilize recirc because there can be hundreds of feet between your central hot water plants and your fixtures. We can accommodate this by using the concept of a swing or loop tank. Here's a diagram from the California Energy Commission's prescriptive method of doing a centralized water heater setup in a multifamily building. This uses multiple heat pumps and multiple tanks in series to perform the main hot water lift, then a smaller electric resistance water heater or loop tank to take care of the hot water recirc load. This is a proven method that works very well in multifamily situations and can even be adapted to smaller scale situations if recirc cannot be avoided. In the next and final chapter, we'll take a closer look at using SANCO2 systems for whole home heating and combination heating and hot water setup, and further cover installation specifics.